Okay, and so this lecture we're going to start chapter 10, which is over bonding models. And we're going to talk about, well, there's three different ones covered in this chapter. One that's called VSEPR, VSEPR. It's an acronym, stands for Valence, Shell, Electron, Pair, Repulsion. And then this chapter also covers hybridization, also called valence bond theory, and it also covers what's called MO theory, or molecular orbital theory. So we'll cover VSEPR theory right now. And so what's the simplest? Hybridization is more complex, and molecular orbital theory is very complex. Okay, so for the VSEPR model, so basically it just tries to predict the 3D shape of molecules. So if we take a molecule like BeF2 or COBF2 or CO2, so in order to use the VSEPR model, you have to be able to draw a Lewis dot structure. So beryllium's got 2 valence electrons because it's in group 2. Fluorine's got 7. So there's 16 electrons to build that molecule. Or for CO2, carbon's got 4 valence, oxygen's got 6. So 16 electrons to build that molecule as well. So for BeF2, if you drew a Lewis dot structure, you would come up with that. So that's 2, 4, 6, 8, 10, 12 electrons in non-bonded electrons and 4 in bonds, so that's 16 electrons. So beryllium doesn't have an octet, but that's okay. It's okay to have less than 8, but not okay to have more than 8 since it's a group 2 metal. You could have come up with this structure as well. So if you took a lone pair and made a double bond to beryllium, then in this case beryllium's got 8 electrons and fluorine's got 8 electrons, so which structure is better? Well, if you calculate formal charges, this is 0, 0, and 0. And then this would be, so 2 valence minus 0 non-bonded minus 4 lines, so it would be -2, and each fluorine would be +1. You know, so the bottom structure is better in the sense that everything's got an octet, but it's worse in the sense that atoms have formal charges, whereas the top structure, nothing has formal charges. But in any case, either one is fine, but probably the top is better. But what we'll mainly focus on in this chapter is what does the molecule look like in 3 dimensions. So what is the structure of that molecule? So is it linear, like that? Or is it, you know, are the fluorines at 90 degrees to each other? So the acronym valence shell electron pair repulsion, basically what that means is you want to try to maximize the distance between electrons. And so if you want to maximize the distance between electrons, then you would put the 2 fluorines not 90 degrees to each other, because then the electrons are too close in space. You would put the 2 fluorines 180 degrees apart. So if you have a central atom with 2 things attached, then it'll be a linear molecule. So we could do the same thing for CO2. So if we drew CO2, carbon's double bonded to 2 oxygens, and then each oxygen has 2 lone pairs, so that's 16 electrons, and all atoms have an octet, and all atoms have 0 formal charge, so that's the right Lewis structure for CO2, and it would be a linear molecule as well. And so I've given you a handout, so I emailed it to you, this VSEPR table. And so if you look at how to read this table, so if you have a central atom, so like here, and it's got 2 atoms attached and no lone pairs, then the arrangement of all of those atoms is going to be linear, and the geometry is going to be described as linear as well. And so then we'll also be looking at bond angles in this chapter. So the bond angle between fluorine, beryllium, and fluorine, or oxygen, carbon, and oxygen, obviously would be 180 degrees. Okay, so if you have a central atom with 3 things attached, like BH3. So how do you, so if you put the boron in the middle, so boron's got 3 valence electrons, hydrogen's got 1. So you only have 6 electrons to build that molecule. So if you put the boron in the middle, then attach 3 hydrogens. Well, so does the molecule look like that? If it looked like that, then it would have 90-degree bond angles. But that's not the way to maximize the distance between 3 things. If you want to maximize the distance between 3 things, you would put them like that. So if you sweep out 360 degrees, and then if you cut that into 3 different quadrants, so that would be 120 degrees, 240 degrees, and then 360 degrees. So if you want to maximize the distance between 3 things around the central atom, you put them 120 degrees to each other in the same plane. So that's a perfectly flat molecule. So in reality, what this molecule looks like is that, where the bond angles are 120 degrees. And so that geometry is called trigonal planar. Okay, so if we take NH3, so a nitrogen with 3 things attached, but it's not linear, it's not flat. This is pyramidal. So what's the difference? Why is BH3 flat and NH3 is not flat? And so if we draw the Lewis dot structure for the NH3, it becomes obvious, because nitrogen's got 5 valence electrons, whereas boron only has 3 valence electrons. And then hydrogen's got 1. So now we have 8 electrons to build the molecule here, whereas we only had 6 electrons to build the molecule there. So for nitrogen, so we attach the 3 hydrogens, and then that's 6 electrons. We still have 2 more to go. So then we put a lone pair on nitrogen, and now it's got 8 electrons. So we got the correct number of electrons. You know, so in BH3, boron's not happy. It's only got 6 electrons, but that's too bad. There's only 6 electrons that you have to work with. So boron does not have an octet in this case, but it's still an okay structure. At least it doesn't violate the octet rule by having more than 8. So for NH3, so we didn't quite complete the structure here. It's got a lone pair of electrons, so if we take a 4th thing and add it to nitrogen, then that lone pair electron occupies space as well. And so rather than the molecule now being trigonal planar, that lone pair of electrons would cause some electron-electron repulsion here, and it would cause the hydrogens to squish down a little bit. And so you get a pyramidal structure instead. So if we wanted to try to draw this in 3 dimensions on a 2-dimensional piece of paper, so with the lone pairs there, so we use what's known as a dashed wedge structure. Right, the dashed wedge means the atom is projected back. So for this molecule, from this perspective, so this hydrogen is going away from you, so that would be on the dash, and this hydrogen is coming towards you, so that would be on a solid wedge. So you would have a lone pair, a nitrogen, and a hydrogen. Those are all in the coplanar. And then you would have 1 hydrogen coming towards you out of the plane, and 1 hydrogen going away from you behind the plane. Okay, and so if we go back to this VSEPR table to make sure you know how to read it. So the left-hand column So this is the number of things on the central atom. It could be 3 atoms and no lone pairs, so that would be like BF3. In which case it's going to be trigonal planar. Or you could have 2 atoms and 1 lone pair. So if we took this, and so if this was not there, if there was a lone pair there instead, then when you describe the geometry, you ignore the lone pair and you only look at the atoms. And so that geometry is what's called bent. So an example of that, so that could be SO2, or a molecule that you're familiar with, NO2 minus, if you remember what that's called nitrite. So Lewis dot structure for nitrite looks like that. So that would have a central atom with 2 atoms attached and 1 lone pair. So that would be trigonal. It's a planar. So the 3 things are arranged trigonal planar, but the geometry, you ignore the lone pair and you just focus on the atoms, and that's called bent. Okay, so what if we have 4 things? 4 things attached to the atom. Okay, so what if we have a central atom with 4 things attached? So an example would be CH4. So carbon in the middle with 4 hydrogens attached to it. So carbon, of course, has 4 valence electrons and hydrogen 1. So 8 electrons, so that would be the right Lewis structure. Carbon's got 8 electrons, hydrogen's got 2. So drawn like that, the molecule would look like it has 90-degree bond angles, but that doesn't accurately reflect what the molecule looks like in 3 dimensions. What the molecule looks like in 3 dimensions, if you have a central atom with 4 things attached, it looks like that. And so that geometry is what's called, well, let me sketch it first. So here we have these 3 atoms, hydrogen, carbon, hydrogen, are coplanar, and then you have one coming, so then 1 hydrogen coming towards you and 1 hydrogen going away from you. Or if I drew it like from this perspective, doesn't really matter, could have drawn it like this. It's all the same molecule, it's just rotated differently in space. And so that type of geometry is called tetrahedral. And the bond angles and a perfect tetrahedron is 109.5 degrees. So if we go back up to this VSEPR table, so if we have 4 atoms, so 4 things on the central atom and 4 atoms and no lone pairs, then the geometry is tetrahedral. Well, the 4 things are arranged tetrahedrally, that's what this first column is, and then the next column, the geometry is called tetrahedral, with the bond angles 109.5 degrees. If we had the molecule like ammonia, that's nitrogen's got 4 things attached to it as well, and those 4 things are arranged tetrahedrally, but we don't call that geometry tetrahedral because we ignore the lone pair, and we call that trigonal planar, right? A trigonal base, a trigonal pyramidal, excuse me. But the bond angles in NH3 is a little bit, it's not a perfect tetrahedron anymore because of the lone pair. And so the bond angles in NH3 are about 107 degrees. So the lone pair is more diffuse because the electrons are not directed between 2 nuclei, so they're more diffuse, they take up more space, and that causes more electron-electron repulsion, which squishes these bonds down a little bit. Or if we had a molecule like water, so again 80 electrons, so if we drew water Lewis dot structure, so that would be a perfectly fine Lewis dot structure, but again it doesn't accurately represent what the molecule looks like in 3 dimensions. So anytime the central atom's got 4 things attached, those 4 things attached are arranged tetrahedrally, just like in CH4. But we don't look at the lone pairs when you describe the geometry. Again, you just look at the atoms, so if you ignore the lone pairs, that would be called bent. And if we drew that molecule, so it would look like that, where we have a lone pair of electrons coming towards you, and the lone pair of electrons going away from you. And so again, if we go back to the VSEPR table, so 4 things attached, but if you have 3 atoms and 1 lone pair, so 3 atoms and 1 lone pair, then the 4 things are arranged tetrahedrally, right, just like CH4. But we ignore the lone pair, and when we describe the geometry is trigonal pyramidal, and the bond angle is a little bit less than 109.5. And so 4 things attached to the central atom, but 2 atoms, 2 lone pairs. So those 4 things are tetrahedral, but the geometry is called bent, and again the bond angle is going to be a little bit less than 109.5. Right now that there's 2 lone pairs, they'll squish the bonds down even further, and so in water the bond angles are about 104.5 degrees. Okay, so if we go back to this table, so compare these two. There's 2 possible scenarios if you have 4 atoms and no lone pairs. So 4 atoms, 0 lone pair. Those 4 things could be tetrahedral. Or 4 atoms, 0 lone pair. Those 4 things could be square planar. So how do you know if it's going to be tetrahedral or square planar? So it's determined by the central atom. So the central atom, if it's a nonmetal, it's going to be tetrahedral. If the central atom is a transition metal, then it could be square planar. Okay, so what if you had 5 things on the central atom? So like PCl5. So phosphorus with 5 valence electrons, chlorine with 7, so that's 40 electrons. So if we drew PCl5, so PCl5 looks like that. And this geometry is called trigonal pyramidal. And the bond angles. So if you notice, so there's a bond angle here from chlorine to phosphorus to chlorine. So that's 180 degrees. Or if you go chlorine to phosphorus to chlorine, or here, or here, or here, here, or here, then those bond angles are 90 degrees. Or if you go from this chlorine to phosphorus to chlorine, right, those will be 120 degrees. So this geometry has 3 different bond angles. And if we had a molecule with 6 things on the central atom, like SCl6, then that molecule would look like this. So we have 180 degree bond angle there. And then these are all 90 degrees. And then a bunch of 90 degree bond angles. So 2 different bond angles there. And that geometry is called octahedral. And again, you see that on the VSEPR table. If you have 6 things on the central atom and all 6 things are atoms and no lone pairs, then they're arranged octahedral, and the geometry is called octahedral with 2 different bond angles. Okay, let's take one more example. So what about a molecule like S? Let's see. I think. No. What do I want? This. SF4. So if we drew SF4, so sulfur, 6 electrons, fluorine, 7 times 4, so 34 electrons. So if we put sulfur in the middle, attach the 4 fluorines, give each fluorine 2 lone pairs, or 3 lone pairs, and that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 12 lone pair. Is 24 electrons, and 4 bonds is 8 electrons, so that's 32 electrons. So we need 2 more electrons. Where do they go? Well, sulfur is a 3rd period element, so we can have an expanded octet, so the lone pair can go on sulfur. Now it's 34 electrons. So that would be the Lewis dot structure. So again, in order to use this VSEPR table, you have to be able to draw a Lewis dot structure. So we have a sulfur central atom with 4 atoms and 1 lone pair, so 5 things total. So 5 things, so it's going to be one of these, but we want that one, 4 atoms, 1 lone pair. And so this geometry is, so the 5 things are arranged tetrahedrally, but we only have 4 atoms now. And one of these is a lone pair. So the lone pair is there. And that geometry is called Seesaw. So the lone pair is here, so it's a seesaw because it looks like a children's toy, right? So the lone pair is here and not there, because if it was there, then there's more electron-electron repulsion. So again, the molecule adopts a geometry that minimizes electron-electron repulsion. So it's better to have the lone pair here, where it's got 120 degree bond angles, rather than here where it would have 90 degree bond angles.